So this introduces me. We are still looking at now, we are now coming to solubility of sparingly soluble salts. You can call them electrolytes. In our previous discussions, we have been looking at solubility of soluble salts, salts that are completely soluble in water. Now we are looking at solubility of sparingly soluble salts. But before that, I want us to go through what we call the concept of dynamic equilibrium. Of a saturated salt solution. So that we get that concept before we proceed to this. Now you are aware that in any saturated solution, what we have there? We have an excess of undissolved solute. We have an excess of undissolved solute or salt. That salt is in contact with the solution in which it is. And that solution is saturated. There is always an equilibrium that is established there is always an equilibrium that is established. Okay? There is always an equilibrium that is established between the undissolved solute and the dissolved solute. So this is what I mean. We have a saturated solution. In which saturated solution we have the excess undissolved solute. It is always in equilibrium with the solution. And that equilibrium is what we call the dynamic equilibrium. We have a container, we have the solution, we have the solute that is undissolved, the two are in equilibrium. We are calling that the dynamic equilibrium. So how is that dynamic equilibrium obtained? In the container, these undissolved solutes come to the surface of the solution at the same rate as they are dissolving in the solution. Some of them tend to come to the surface of the solution here. This is our solution, as others are remaining within the solution. So the tendency of them coming to the surface of the solution, in that case, if we find that it is equal to the tendency at which they dissolve in the solution, that's when we establish what we are calling a dynamic equilibrium. And at that point, the amount of solid dissolving balances the amount of substance that is crystallizing or that is coming to the surface of the solution. So you need to understand that concept of dynamic equilibrium of a sparingly soluble salt. Now, what is a sparingly soluble salt? We shall be using these terms concurrently in this topic. Sparingly soluble salt or electrolyte. From your O level, you are aware that all carbonates, you said that all carbonates are insoluble. apart from sodium carbonate, which other one? Which carbonates do you say are soluble in O level?
Ammonium carbonate.
Said potassium carbonate, ammonium carbonate, and sodium carbonate are all soluble, but all other carbonates are insoluble. Okay, that's what you said. You said all other carbonates are insoluble. At O level, we are modifying this, and we are saying all other carbonates are sparingly soluble. Why am I using the term sparingly soluble? Although you could have been told that calcium carbonate is insoluble, at some point when you put it in water, there is some of it that tends to dissolve. So all these salts that you say that is soluble in water, the calcium carbonate, the silver chloride, the lead 2 sulfate, the calcium sulfate, that one you said it's sparingly soluble, and others, they are not completely insoluble in water. Actually, there is no substance that is completely insoluble in water. That's what studies show. That's what studies show. There is no any known substance that is completely insoluble in water. Some of them tend to dissolve in water to a smaller extent, such that their solubility cannot be determined by the experiment we have seen before. You remember that experiment we saw for determination of solubility of completely soluble salts. So these salts that are only partly, or that are only soluble in water to a very small extent, are what we call sparingly soluble salts. Are we together? Now, these sparingly soluble salts, their solubility is determined by what we call, their solubility is determined by a constant, which we call the solubility product. Solubility product is normally given the abbreviation KSP. How does it come about? Let's consider a sparingly soluble salt. Consider a sparingly soluble salt. And that sparingly soluble salt is AXC BY. Let's assume that's our salt. If you dissolve it until you form a saturated solution, the ions in this salt will be, the ions of the electrolyte will be in equilibrium with the undissolved solute at a given temperature. And the equation for its solubility will be given as AXC BY. Remember, it's a solid. Aqueous, don't put brackets on this. In a solution, there is an equilibrium established between this salt and its ions. What's the charge on A? The charge on A is the valence here, which is Y plus. Is the cation. And that of B will be X minus. Are you getting me?
Yes, teacher.
Now, from the law of mass action, from what we call law of mass action, you'll find that the solubility constant here is given as the molar concentration of the AY plus ions multiplied by the molar concentration of the BX minus ions divided by the molar concentration of the salt itself. That is the solubility constant. However, there is an assumption that is taken here. Which assumption do we take? The assumption is that solubility of this compound, the solid, remember this is a solid, according to this equation. The solubility of the solid remains constant. After all, it's sparingly soluble. So since it remains constant, what happens? What happens is that we take it to be a 1 since it's constant, such that our solubility expression becomes K is equal to the concentration of Y plus, that's molar concentration of Bx minus over 1. So this becomes a solubility constant, which we call KSP. And this KSP is what we term as the solubility product constant of any sparingly soluble salt. From that, we shall get its definition. What's the definition of solubility product? Solubility product is the product. Look at this expression. It is the product of the molar concentration of the ions. Product of the molar concentrations of the ions of what? Of a sparingly soluble electrolyte in its saturated solution. Raised. Oh, I forgot something here. Remember from our equation, it was AXBY solid plus aqueous. This is giving us A Y plus aqueous plus B X minus aqueous. This equation wasn't balanced, it must be balanced. How do you balance it? By putting an X here and then putting a Y here. So something I forgot here, we should have powers here. Which power should be here? The power that should be here is this X. The stoichiometric coefficients in the equation. So we should have the power X here and the power Y here. We had forgotten that. Such that now the solubility product is the product of the molar concentration of the ions, of a sparingly soluble electrolyte in its saturated solution, raised to appropriate powers. At a given temperature. At a given temperature, raised to appropriate powers at a given temperature. So what are the key points that you shouldn't forget in this definition? Product of the molar concentrations of the ions. Which ions must be for a sparingly soluble electrolyte, which is in its saturated solution. This is very important. Raised to appropriate powers at a given temperature. That's the definition of solubility product. Now, finally, I want us to look at how do we write expressions for solubility product. How do you write expression for solubility product? How do you determine write expressions for solubility product? Expressions for KSP. These ones are only known if you know the equation. Let's consider the following sparingly soluble electrolytes. The first one is silver bromide. Silver bromide is sparingly soluble. So if I'm to write the equation of silver bromide dissolution in water, it will be this equation. It will be that, giving me silver ions have a valence of 1, and then bromide ions. That's the equation. For its solubility, if they ask the equation for solubility of silver bromide in water, that's the equation. Now, what's the expression for the solubility product? Know the difference between the equation and the expression. The expression now becomes molar concentration of silver ions, which are here, multiplied by the coefficient here, which is 1, multiplied by the molar concentration of the bromide ions, multiplied by the power here, which is 1. Are we together?
Yes,
Yes.
teacher.
That equation is 1 mark and that one. If I consider another sparingly soluble electrolyte, for example, silver ethane dioate, silver ethane dioate, sometimes called silver oxalate. Silver oxalate, its equation will be, you should know the formula, silver C2O4. That would be the equation. But remember, the oxalate ion has a charge of -2. So this formula is not correct. You must be very careful here. What do we do to make it correct? What we do to make it correct is to write a correct formula. How will that correct formula be written? The correct formula becomes silver 2 C2O4 solid plus aqueous. Remember, we said we don't put brackets on the aqueous, it's not a state, it's showing dissolution. So this will give me silver ions. I should have a 2 here to balance the silver ions plus the oxalate ions. 2 minus, there is aqueous here, such that my expression for KSP is silver ions square brackets squared into oxalate ions charge 2 minus power 1, because the coefficient here is 1. Are we together?
Yes, sir.
So this should give you a mark there. The next compound I'm lastly looking at is that of calcium phosphate. The valence of the phosphate radical, the charge on the phosphate radical is 3, and that on the calcium is 2. That is a solid plus aqueous. When you write a wrong formula of the compound, you can't write the correct equation, and you can't have a correct KSP expression. This will be calcium 2, shall have a 3 here, plus 2 phosphate radical has a charge of -3 aqueous. That's the equation, such that our KSP is equal to molar concentration of the calcium ion power 3, molar concentration of the phosphate ion power 2. Are we together?
Yes, sir.
So that's all about writing equations for solubility of the sparingly soluble compounds and their expressions for solubility product. Those with the books, you have questions about writing expressions, both equation for silver chloride, silver iodide, silver carbonate. Try out all those ones. Calcium ethane dioate, chromium 3 hydroxide, very many others. Lead 2 iodide, all these are sparingly soluble. Lead 2 chloride, we have lead 2 sulfide, we have manganese 2 sulfide, so many others. We have calcium, hydroxide. So I want you to get free time and try out both equations and solubility product expressions for all those sparingly soluble salts. There are about 39 of them. Try them in your free time. The next time we meet, we shall look at conditions under which solubility product is valid and experiments to determine solubility product of different experiments. Subscribe more to our YouTube channel and watch more of these lessons. Nice time. Thank you for attending this lesson. Have a good day.
Thank you, sir.
Welcome.
Thank you.
You're welcome.